Good morning, students. Welcome to the today's class. Today, we'd like to discuss about lecture number 3 in unit number 4. So, we would like to discuss about alternative forms of alternative Cmos design. Alternative Cmos design. Okay. So far, we have seen that NMOS transistors has got a problem of static power consumption when both the transistors are on. So, but if you go for the CMOS, both the transistors are on, possibility is very less. Okay, therefore the static power consumption will be less. Okay, so but the number of transistors to implement the circuit is very, very high. Okay, so that means how many number of NMOS transistors you should take, those many number of PMOS need to be taken. Okay, so that's what we have to identify. So another alternative way is that pseudo-NMOS logic approach. Pseudo-NMOS logic. So let us do quickly. Let us understand quickly about this one. So what is the circuit look like? So here we have to consider that a PMOS transistor we have to take it as a pull-up network. Okay. PMOS transistor, I should take it as pull-up network. Okay, so this is what the pull-up network we have to consider, and the pull-down network must be an NMOS transistor, NMOS block. So this is how we have to consider. Therefore, take a common point between these two, and that is called output Y, and this is connected to ground. This is connected to VDD. Most importantly, we need to know that this is always on. If you want to make PMOS is always on, what I have to do? I have to connect this one to the ground. So when it is logic 0, the PMOS transistor remains always on. Okay. So now the input we have to give it here. So this is the generalized schematic. Okay. This is a generalized schematic. For example, if I want to implement a NOT gate, if I want to implement NOT gate, pseudo-NOT gate, pseudo-NMOS NOT gate, for example, pseudo. How do I do this one now? So since NMOS block requires only one transistor, therefore we have to consider PMOS transistor we have to take, and NMOS only one transistor I need to consider. Okay, so this is connected to A, for example. We will get here is Y is equal to A complement at the output. This, remember that this must be connected to ground only. This is connected to VDD. This is connected to ground, right? So this is acting as not operation, but in pseudo approach. Okay, so like this, for example, NAND gate, if you consider pseudo-NAND gate, for example, pseudo-NAND gate. What I have to do then, I have to consider a PMOS transistor, which must be always on, and we have to consider two NMOS transistors, something like this, because the NAND gate having, what do you mean by NAND gate? Y is equal to A dot B whole bar. So A and B are connected in series connection, right? This is the series connection. So we have A here, we have a B here. The common point is Y, so it will produce A dot B whole bar. So what is happening here now? So this is actually pull-up network is a PMOS transistor, pull-down network is NMOS transistors, right? Therefore, it is look like it is a CMOS logic implementation. Okay, But original CMOS logic contains, if you consider a NAND gate, two transistors that we have taken, and pull-up also we have to consider. Pull-up also we have to consider another two transistor of p-type. But in the pseudo NMOS logic, what we are doing here is that we consider only one PMOS transistor. So therefore, we have reduced the number of transistors by one. Okay. So whatever the logic function it is, when compared to the conventional or when compared to the basic CMOS logic, the pseudo NMOS logic, the number of transistors will be reduced. Okay, what is the conclusion here? So in the point with respect to number of transistors, with respect to number of transistors, pseudo NMOS offers less in number. Okay, so we have to consider offers less number of transistors are required.
Hello.
Yes. Yeah, tell me.
Sir, ఇలా చేస్తే డిప్లీషన్ కి దీనికి తేడా ఏం లేదు కదా సార్ అలా అంటే
I will tell you.
Sir?
So yeah. So actually when compared to the depletion mode type of transistor, the size is large when compared to the PMOS transistor. Okay, the length is actually 4 times that we have to consider. Okay, and one more thing is that the length of the length is 8 lambda that we have to consider. It doesn't require 8 lambda. Okay, so it contains less. The area point of view, it is very less when compared to that one. Okay, so depletion type mode transistor consumes a lot of power because of its area size. Okay, and delay also very high because of input capacitance of the depletion type mode transistor is more than that of PMOS transistor. Okay, so that's it. So but it is also observed that it is also a ratio logic. Okay, that means if you want to have a output high value or output low value, the ratio of the NMOS and PMOS is required. Generally, if you want to get, for example, if you take a conventional CMOS logic style, okay, it doesn't require the size of this NMOS and PMOS transistor. Okay, if 1:1, you take 1:1 also, it doesn't matter. Okay, you'll get better out. You'll get the output is better. It does not depending upon the ratio of this one. Whatever the VOL, whatever the VOH, output low value, output high value, does not depending upon the ratio of the devices. But whereas this approach is depending upon a ratio of the MOS transistors. Why? Because so here if you see at any point of time, at statically if you apply 0, you'll get logic high value only we will get. Okay, that time only one transistor is on. Okay, if you apply logic 1, again it's depending upon only one transistor. Logic the logic low value will be generated. Sorry, logic low value will be generated. So since both the transistors are on, possibility is very less in general CMOS approach. But in this particular approach, when you make A is equal to 1, for example, here, okay, both the transistor becomes on. Why? Because PMOS is always on, right? So therefore, yes, as our friend told, raised a point is that what is the advantage of that one? So one point is that yes, obviously the size of the depletion is more than that of the PMOS transistor. That is a one point. Another point is that how much ratio that we need to maintain. Okay, whether it is equal to that of the depletion or maybe less than is there. That's what we have to investigate. So let us now consider that. So let us now consider. So what happened if what are the conditions of both the transistor that you observed there? Any guess? So how do we calculate the ratio of the device? Anyone from the class? How do we generate the ratio of the device? What methodology that we have chosen in the previous classes? Anyone from the class?
Sir, we use lambda, that value.
No, not like that. So we have used the concept called an inverter is driven by another inverter concept, right? An inverter is driven by another inverter. So that what the point is that whenever Vn is equal to transferred to as a V out, okay, so that must be also equal to Vn, because of here we generate the V intermediate signal called VNV, for example. So that will be transferred here. The same Vn has to be generated. If the V out is not equal to that of Van, then obviously our attempt to generate the implementation is wrong. So therefore, what is the size of this device we have to maintain? That's what important. Okay, so if you want to do this one, again, the same setup we have to follow. So we have to consider a depletion, sorry, a pseudo-NMOS transistor for the case of simple implementation. This is called, for example, this is very good to understand that it's a VAN, for example. VN, it is called VADD. Connect this as an input to the another pseudo NMOS, right? Something like this. We will get an output is called V out, right? So that is what this is what it is saying in this way. Okay, so two inverters are connected in cascaded fashion. So the moment at which when Vn is equal to middle of the point. Okay, so what is the consideration? So I want to make both the transistors on. So I want to make both the transistors are on, means this input voltage must be VDD divided by 2. Okay. So therefore, what we have to observe here also, VDD divided by 2 will be observed there. So when the input of this one is VDD divided by 2, then both the transistor becomes on. Okay. Now the point is that what is the operating mode of this one? What is the operating mode of this one? We should know. So as soon as it is NMOS transistors more than that of the threshold voltage of NMOS transistor, this will be entered into saturation region, as we have studied extensively this approach. Okay, then this transistor will be in the resistive region or linear region. This will be in linear region. Okay, so therefore these are the two important points that we should know. So once we know that the current equation, I linear current equation, IP of linear current equation of PMOS transistor, IN of saturation current is of these three equations must be equate and get the relationship between these two. Okay, so because of lack of time, actually we have done this processes very well in the previous classes. So I want to take a direct equation from the textbook. Okay. So if you do this one, please go through it once in your pull-up transistor. One inverter is driven by another inverter. Pull-up to pull-down ratio of one inverter is driven by another inverter. Concept is there, no? So that's what we have to refer once. So there I have mentioned there. So if you equate these two things, this is what the input. This is what we will get the equation. The current equation, linear current equation of the PMOS transistor, saturation current equation of the NMOS transistor we have to consider. So this is what we have to do. So what are the typical values that we have to consider there? So what are the typical values that we need to consider? This one. So the typical values are, in this equation, if you substitute these typical values, these are called typical values. Okay, so then what is the final ZPU divided by ZPD we will get there? Now, if you substitute all these things in the above equation, ZPU divided by ZPD is equal to 3:1, we will get there. 3:1, we will get there. So what we observe for the depletion type mode transistor, we maintain 4:1 we got for depletion. Is it clear? Okay. So if you do this kind of ratio, what advantages we can get than that other depletion type then. Okay, so very important thing is that if you are maintaining this relationship, that is the pull-up network is actually 3:1 ratio, and this is 1:1, for example. Okay, can you define what is the power consumption of this device? Can you define what is the power consumption of this device? What is the R on for this one? What is R on? If you guess, if you calculate this one, this value will be 85 kilo ohms. 85 kilo ohms with the given ratios. But here it is a 50 kilo ohms. It is 50 kilo ohms. R on for this one is right. Therefore, if the on resistance of the device is more, what expected to the static power consumption, power dissipation that we have seen in the previous class. Okay, how do we calculate the power dissipation? Power dissipation of the given circuit is equal to, so it is inversely proportional to that of the ratio of R on. That's what we calculated previously. It is inversely proportional to R on. So if the bottom, if the denominator dimensions are very, very high, 85, than that of the 50, automatically power consumption will be reduces. Okay, so if we calculate and compare this one, we can say that 60% power reduction can be possible with the given ratio. Okay, that means substitute 85 in the denominator, 50 in denominator in the given power consumption formula. Okay, then we'll observe that 60% power saving can be possible by using the pseudo-NMOS logic compared to the depletion mode type of transistor. Okay, so what we have done here is that our main objective for this CMOS implementation, previous CMOS implementation, is that more number of transistors are required. So in order to do this one, we have to use the pseudo-NMOS logic. In this pseudo-NMOS logic, what we found that, yes, the ratio is 3:1 we are maintaining. Therefore, but anyway, if you go to this one, it's depending upon the ratios. Okay, so in spite of less number of transistors, the output values are depending upon the ratio of the circuit. Okay, that's the one point we have to remember. So the first one is the general CMOS. So normal CMOS versus a pseudo-NMOS. So what we observe that, what is the main thing? Main thing is that less number of transistors. But what is the biggest disadvantage of this one? Ratioed logic. Output అనేది ratio logic may depend out అనేది, it's not advisable one. Okay, we have to carefully design the size of the transistors, otherwise we won't get the output properly. Okay, that's the thing. So when compared to the pseudo 2, number B, when compared to the pseudo 2 versus depletion, okay, so what we observe, so pseudo requires, so this requires, actually this is what advantage we are talking about. So then we'll write it as a depletion versus of pseudo. So therefore the pseudo has got less power consumption. It offers less power consumption or dissipation. Right? How much the less power? 60% power consumption can be reduced. I hope you understand the concept of this pseudo-NMOS logic, right? Fine. Let's move to another concept. That is, okay, we find that there's some difficulty in it. So another approach is called dynamic logical circuit, dynamic CMOS logic. This is the approach let us consider it now. Okay, previously we talked about pseudo-NMOS logic. Now we would like to discuss about dynamic logic. Okay, so what is there here is that I'm going to consider what is the generalized schematic in this approach. In this approach is, So I don't want to consider both the transistors are on by applying the input signal. Okay. So I want to convert it into CMOS logic again by using this approach. So we have to use a PMOS transistor at the top, and we have to consider NMOS transistor at the bottom. Okay. So take a common point here. So this is called F5, we can call it as. Okay. Now we are going to apply NMOS logic in between. So if a pi is applied to the top transistor and bottom transistor, means if this is 0 means upper one is on, if this is 1 means bottom one is on. Okay, so there is no possibility of both the transistors are on at the same time. Okay, that's how we want to eliminate the problem of making the both the pull up and pull down is on at the same time. Okay, so now the connections are something like this. Take a common point here. Okay, and connect this one. Connect this one to the ground, connect this one to the VDD, connect this is all Y. So apply the input signals here is that apply the input here, something like this. Is it right? It is a generalized structure. It is a generalized structure. Okay, so if you want to perform a NOT gate, okay, so it is possible to implement the NOT gate there. Okay, so for example, NOT gate, let us consider. So it does not depending upon the ratio then. It won't depending upon the ratio. Okay, please remember that point. So PMOS transistor, one NMOS transistor is required, another NMOS transistor is required. So these two are connected, and this is called common clock. Normally we can call it as a clock signal phi. And this is an input A, we will get output Y. This is called VDD. Okay, so very important observation is that, so operation, let us consider it an operation. See, here in a dynamic logic CMOS implementation, the PMOS has a different role. Top PMOS transistor has a different role, and the remaining part is another role. Okay, what we do is that it follows the approach called pre-charging, and second one is called evaluation mode. That means the circuit is operated in these two modes. The circuit is operated in these two modes. It is in the pre-charging mode, or it will be in the evaluation mode. What do you mean by the pre-charging mode? Okay, so the pre-charging mode is nothing but, so by what do you mean by this one? Which means that when phi is equal to 0, okay, then what is happening here? It implies that PMOS is on. PMOS is on. In that case, what about NMOS? NMOS is off. So NMOS, bottom NMOS, this is off out. This is off out. This is on out. Then by making this one is equal to logic 0. So if the bottom transistor off means A transistor is also off. Okay, this is also off. This makes this transistors off. So therefore the Y is charged to VDD. This is called pre-charging mode. This is called pre-charging mode. Right? Then what do you mean by the evaluation mode? That implies that Y is equal to VDD. That's what happening there. So therefore, whenever you are using the dynamic mode, first you have to pre-charge the output nodes. First, what you have to do? First, you have to pre-charge the output node fully by using the PMOS transistor. That is what you have to do. The second one is evaluation mode. So by applying the input signal, we have to calculate what exactly the output is, right? So therefore, when phi is equal to 1, logic 1, then what is happening here? If phi is equal to 1 means PMOS is off, but only A transistor is on, okay, and bottom transistor, Okay, so let me call it as a T2 on the T1 on the T2 and T3, for example. So T1 is on, T2 is also on, both are on. So T1 comma T2 both are on. So whatever the output that you see here, that is your actual output. Whatever the output that you see here, that is what your actual output. Okay, so therefore the output Y is equal to, what is the output Y? Output Y is equal to ground value. So that is how we can get the output value over there. So therefore, so if both are on. So I'm extremely sorry. It's not, we cannot decide that both are on at the same time. Okay. So when phi is equal to 1, now if say A is equal to 0, what is happening here? Y is equal to VDD itself. It does not change because both are bottom transistors are off transistors only, open circuit. If A is equal to 1, now we can say that Y is equal to ground. Am I right? So therefore, this is what important. So that this is what evaluation phase of the transistors. Okay. So, but very problematic situation is so far so good. Okay, it does not depending upon the ratio logic. Okay, because pull up and pull down are both are independent. Okay, depending upon the input signal. But the problem here is that it is not possible to cascading cascading by the single clock. Okay, so single phase clock antam din single phase clock. So by using this one, it is not possible to do this one. Why? Because okay, for example, you consider this one, right? Okay, copy, paste it here. So here. Okay, so for example, I want to cascade another device. So I want to cascade this one to this one. Okay. So what I will try to do is that the output of this one is connected to input of this device, right? The output of this one is connected to input of this one. Okay. So what is happening here is that whenever we are doing the pre-charging phase, okay, that means whenever you want to pre-charge all the transistors, what is our primary requirement? We have to pre-charge the output nodes. So we have to pre-charge this one, we have to pre-charge this one, we have to pre-charge every output node. During the time, what is happening here? During the time, what is happening here? The output of this one is connected as an input to this one. That means A is evaluated. So therefore, while you're doing, very important thing is that while you're doing the pre-charging, evaluation should not be happening. Okay, it is mutually exclusive. That means the pre-charging jarugutunnappudu evaluation jaragakudadu, evaluation jarugutunnappudu pre-charge jaragakudadu. It shouldn't be happen. So but what is happening here? When you're doing the pre-charging of the first inverter, first the inverter pre-charge chestunappudu ademoutundi, the output will be changes to VDD, right? That change is activating this transistor T1 in the second stage, right? Agreed? So because of that one, the scenario will be changes. Okay, therefore, whatever the pre-charging value is there, that is cannot be sustained here because of this is active on. So because of this, the change of the, for example, the Y1, because of the change of the Y1, it is affecting the the transistor T1 or maybe A. For example, A2 anukunnam then. This is A1 anukunnam. So Y1 is activating. Y1 is affecting the. Y1 affects the A2 while pre-charging Y2, right? Y2. So it should not be happening. Okay. So therefore, this is the problem. This is the problem. So therefore, this problem has to be avoided. That means that whenever you do the pre-charging for all the nodes, evaluation should not be happen for anything. So in order to do this one, two approaches are there. So one approach is two approaches. Number one approach is use different clocks. Use different phase clocks. For example, phi 1 తీసుకున్నాను, phi 2 తీసుకోండి. Phi 2, you have to take phi 2. So like this, different phase clocks you have to consider. That is the one thing. The second point is that we have to use um, transmission gates at the output. That is what we have to do. So by using the different clock means, of course, I can show you that what kind of clocks that are necessary to do this kind of approach. Okay, so these are the clock signals. I will show you this one, copy and then paste here. See here. So these are the different clocks I have to consider for each and everything. Okay, that is the one thing. Okay, otherwise you use the transmission gates at the output side. So what is the transmission gate we normally consider in this way? So you consider that one only. We have a pull-up network. This is the approach number A, this is approach number B we consider. Of course, here also we use the multiple clocks only. Single phase clock is not at all suitable for implementation in a cascading fashion, right? So this is what we have tried. The output, see, the output of this one is connected to transmission gate. This is what the transmission gate. What do you mean by the transmission gate? I will tell you this one. So we have a PMOS transistor. We have an NMOS transistor. Connect both the things, and this is called a transmission gate. Okay, so here is we have to consider the different clocks here. Here also we need to consider the output. We have to consider here itself. Okay, so it is an NMOS logic, something like this. So we use the different clocks by introducing this extra thing. Okay, we have to introduce this one. So what is the clock things that we have to do is here is that we have to take 512 bar. Okay, and we have to take 523 bar 523. So what do you mean by this one? I'm saying that, for example, here you consider it this way. So this kind of approach will make sure you that while you are precharging the succeeding stage, this cannot change the NMOS block in the succeeding stage. Okay, so normally 51, 52, 53 are the clocks that we need to consider. So 512 is generated from clock 1 to clock 2 by simply OR operation. This is a low, this is low, therefore this is a low value is here. It is high and this is low. So OR operation between these two, we have to do it here. And this is a high value, this is a low value. We have a high value. So like this is an OR operation. Therefore, this clock is required for this one. Okay, so like this, a different approach, different clocks we need to generate. Which one is more suitable to avoid this kind of scenario that we have to use. Okay, so this is what we have to consider in our structure. So what is the complementation of this one? So simply it is low means it is high. It is low, high, and low. So that's what I'm writing here. So this low means high. This high means low. This is low means high. This is high means low. So therefore, that is what the scenario we have to consider for this. Okay. So therefore, this is one approach by which it is possible to cascade. So therefore, what is the main conclusion that we have to draw here? It's a note is that note. By using single clock, by using single phase clock, why it is not possible to cascade dynamic logic circuits, dynamic logic circuits. Hence, we have to use multi-phase clock. Multi-phase clock. Right? Agreed? So this is what important. Multi-phase clock is important for us. Okay? That's approach. So in order to avoid this problem, okay, I don't want to use the multi-phase clock. Okay, but same situation is that why should I use the multi-phase clock? Because it is the generation requires another kind of hardware is required for that one also. Okay, instead another better approach is there. So that approach is called domino logic. Domino logic. Here it doesn't require any kind of multi-phase clock. Instead, we use an inverter at the output. We should use inverter at the output. That means we have to consider the same only dynamic logic circuit only we have to consider it, right? Okay, consider this. This is called phi. This is called NMOS logic. Okay, connected here. And VDD, this is here, the ground here, of course. And this is called phase clock phi. The very important point is that we have to consider a NOT gate at the output. We have to use the NOT gate. So this is the NOT gate is required for this one. So now this doesn't require any kind of thing, but provided that it's very important to note that the output is uncomplemented output can be possible. Here you can see, we can see uncomplemented outputs. So normally CMOS approach always gives you complemented output, but because of this one, uncomplemented outputs can be generated. So any uncomplemented output can be generated by using this one. Okay, so therefore this approach give you the cascading connection of this one. It does not give you any kind of impact on by using this NOT gate. Okay, so therefore the problem with the dynamic logic circuit is well addressed by the domino logic by just introducing the NOT gate at the output side. Okay, which is used to restrict the succeeding stage, the evaluation phase while pre-charging that stage. Okay, so the pre-charging can be restricted by using this one. Sorry, evaluation is restricted by using this NOT gate while pre-charging the succeeding stage. Okay, so therefore if in the examination maybe people will ask a domino and NOT gate. Domino NOT gate, if you ask it to write domino NOT gate, you are in a position to write. Okay, domino AND gate. AND gate can be possible, OR gate can be possible, NAND gate can be possible, NA and NAND gate. So all these things that you have to try to do it on your own. Okay, because just you have to use the NOT logic only implementation here. So another important one is C-square-MOS logic. C-square-MOS logic. This is called clocked CMOS logic. So this is also another implementation in a CMOS logic. What we do here is that here we use PMOS logic, and of course we use NMOS logic. We use NMOS logic. Okay, so this is called VDD. This is called ground. Now what we have to do is that we have to consider a PMOS transistor at the output node and NMOS transistor at the output node. This is what we have to do. So by let me check clock bar and clock. So this is called clock bar and this is clock. So this approach is called clocked CMOS. Okay, that means as many number of NMOS transistors are there in the NMOS logic, those many number of PMOS are required. Okay, but that was connected in series. Sorry, if it is in series, that is in the parallel. But in the middle of this one, we have to use this clock signal. So when this operation will be performed, when phi is equal to 0, what is happening here? when phi is equal to 0, upper transistor is on. Okay, bottom transistor is off. Therefore, what is happening here? Therefore, T1, let me consider T2. So T1 is on and performs the pull up network active. Okay, so that's what happening. When phi is equal to 1 and T2 is on, during this one, T2 is off. During this one, T1 is off. Then pull down network is active. Okay, so this is the approach makes sure that both the transistors pull up and pull down network is on. On condition is rare. Okay, by using the clock signal. Okay, so that's what our requirement is. So at a time, both the networks should not be on. Okay, so in order to restrict this one, we use the clock signal, something like this. It is possible to make sure that both the things are off. Are they agreed with me? Okay. For example, for sake of simplicity, let me write NAND gate, C squared MOS NAND, for example, NAND. So how do you write like this? So for example, what we know that, so PMOS transistor, NMOS transistor connected in series connection, right? Okay. So, but PMOS transistor connected in parallel. Obviously, you may identify that there is a number of transistors increases, but you will have a good output logic based on the clock signal when compared to these things. Okay, therefore this is called A. For example, this is called A. This is called B. This is called A. This is called B. And the bottom, in this one, we write a PMOS transistor here and NMOS transistor is here. Okay, this is called phi bar. This is phi. So you'll get an output is y. Y is equal to A dot B whole bar is possible. Okay, so the operation is self-explanatory. Just by substituting phi is equal to 0 and apply the A signal, B signal, and phi is equal to 1, what will happen? So this kind of things can be self-explanatory. You can do it this one also. And very, very important thing is the C-square MOS logic supports the cascading connection, but more number of transistors are required. So the control manner that we can generate the output by using this one without any ratios. Okay, so the last one is the alternative NNP MOS logic, NP logic. You please go through it in the textbook. Otherwise, I will discuss this one in the next class. So we have to consider that the dynamic logic circuits only. I think better I have to take a figure and do it here. So this is what we normally write NP logic, alternative and NP logics here. Okay, so it is simply a dynamic logics only. Okay, what is this one? It's a dynamic only, dynamic logic only, dynamic logics only, dynamic CMOS only. But in order to avoid this cascading position, what I have to do is that if you consider the NMOS logic, in the next stage should be a PMOS logic. Okay, then this particular device will be off. Okay, that's what we have to understand. So whenever this is, for example, precharging mode, this precharging mode cannot on this PMOS block, because for the PMOS one, if logic 1 is applied, it's off only. Therefore, that's how we have to restrict. Okay, so whenever you're doing the cascading, what we have to do it, if it is an NMOS, PMOS, it should be a PMOS. Therefore, all the nodes are precharged comfortably. All these nodes are precharged comfortably. Okay, so that's how we have to do it. NMOS and alternative NNP-MOS logic can be implemented by using alternative NNP. Okay, so these are the different alternative ways we have to use in CMOS logics. Okay, these are the different ways that we have to implement in a CMOS logic. All right, so the remaining things we will see in the next class. Thank you. If you have any doubt, please send your queries through the modules one. We stop it here today.